In the previous video, you've learned how to compute steady-state probabilities for each state in the system. Now let's look at how we may use these probabilities in decision making. In the column example that we've seen before, we are given this transition probability matrix P. Now we have additional information. It says here that each customer makes one purchase of cola during any week, and there are 52 weeks in a year. Suppose there are 100 million cola customers, and then each cola that you sell costs the company $1 to produce and is sold for $2. Or in other words, the profit for each bottle of cola is $1. And then here it says that for $500 million per year, an advertising firm guarantees to decrease from 10 to 5% the fraction of Cola 1 customers who switch to Cola 2 after a purchase. So this sentence means that the advertising firm says that it can guarantee to decrease the probability of a customer who switched from Cola 1 to Cola 2 within one purchase from 10% to just 5%. But then the question is, should the company that makes Cola 1 hire this advertising firm? Because does this reduction from 10% to 5% worth it or not? Because the company has to pay $500 million per year. And then if you're wondering why we need to use steady-state probabilities to solve this problem, well, one of the clues you can see here that it says it involves a large number of purchases. There are 100 million cola customers and it involves the purchase in 52 weeks. So from here you can say that, okay, this problem is something very big, considering a very big number of purchases. So the n in n steps is very large. It doesn't just talk about 1 or 2 purchases later, but it talks about 100 million purchases in 52 weeks. So that's how you may think that you need the steady state probability to solve this problem. Okay, so from the problem, that's the effect that is promised by or guaranteed by the advertising firm. In one purchase, the probability of a customer switching from Cola 1 to Cola 2 will be decreased from 10% to just 5%. But that is just for one purchase, one step in the term of Markov chain. We need to look at what happens in the steady state when the number of purchase has been very large. So we have seen in the previous video that the steady state probabilities for the cola example, the original example, is 2/3 for pi 1 and 1/3 for pi 2, which means that regardless of what people buy right now, after n purchases and n is large, a person has the probability of 2/3 to buy cola 1 and 1/3 to buy cola 2. When you have the new matrix P, which is called P1 on the right hand side, you may also compute the pi 1 and pi 2 using the step in the previous video, and then you should obtain the value pi 1 equals 0.8. So it is increasing quite significantly. And then pi 2 is just 0.2 now. Now what we need to do is to compare the profit from the current condition to the condition after we hire the advertising firm. From the current condition, the net profit for the company that manufactures Cola 1 equals to 2/3, because 2/3 people are purchasing Cola 1. So this is 2/3. And then the total sales in a year equals this much, 52 weeks, and then 100 million customers per week, and then $1 profit from each purchase of each customer. So this is the net profit for the current situation. And then what is the net profit for the situation if we hire the advertising firm? You may compute it using the same way, but then now pi 1, the probability that a person will purchase column 1 increased to 0.80. So now the profit of the company becomes 0.80 times the total sales in a year. But remember that we need to pay the advertising firm $500 million. So to obtain the very net profit of the situation, you need to subtract the profit that you get from the sales minus the fee that you need to pay for the advertising firm. And then you can see that still the net profit is larger than the current condition. So in this situation, the decision is that yes, we need to hire the advertising firm. Now here's another example. It's about playing Monopoly. I hope you're quite familiar with this game because I'm not sure if kids nowadays are still playing this game. When I was a kid, this was one of the most popular board games, I would say, and I played this a lot. Okay, so here we're going to look at the research of some people that model the monopoly as a Markov chain. And as the result, there are some decisions that may be explained using the steady state probabilities. So let's take a look. So some people compute the steady state probability that a particular player would land on a particular square on the Monopoly board. To be exact, on each of the square on the Monopoly board. So the probability of, let's say, landing on the jail here is 0.1123. It's pretty large if you compare the probability with the others, which is 0.0 something, right? And then what we're going to look at here is that comparison between the orange squares. So these are the orange squares and then the green squares here. Okay, so we are specifically going to look at, suppose you may choose, is it better to build hotels on the orange squares, or is it better to build the hotel on the green squares? So if you want to build hotels on the orange squares, you will need $1,500. So this is the total for building the hotel on these three squares. And then if somebody else, another player, lands on St. James Avenue, which is this, he or she must pay a fee of $950 to you. And then Tennessee Avenue also $950, and New York Avenue is $1,000. So we receive this money if somebody else lands on one of this square, and then you have a hotel there. And then you can say that the expected revenue per dice roll can be computed using the steady state probability, right? Because the steady state probability says that the probability that at any point of time, so at any turn when the dice is rolled, the probability that somebody will land on St. James Place is 0.0318. And then the probability that somebody will land on Tennessee Avenue is 0.0335 and so on. So you may compute the expected revenue per dice roll equals the fee, the hotel fee that you will receive here, times the probability that someone will land on that square. So here's the expected revenue per dice roll, but remember that you also need to consider somehow how much investment you made, right? So finally, you can say that the expected revenue per dollar invested is the expected revenue divided by the amount of investment. So you get this number, 0.064 dollars per dollar invested. Now let's compare with the green squares. If you build hotels on the green squares, you need a higher investment, 3,000. But also, anybody who lands on your property on this green square, they need to pay higher than if they step on your properties in the orange squares. So here you can see that the fees are higher. And then just like before, you may compute the expected revenue using the steady state probability information. Because the steady state probability says that this is the probability that at any step of the game, somebody will land on the square with this probability. As before, to make a fair measurement of the expected revenue, you should divide the expected revenue with the investment that you spent at the beginning. So here it turns out that although the fee that people have to pay when they step on your properties is higher than the orange squares, the expected revenue per dollar invested is actually smaller. Now let me summarize the result. From the revenue, the green squares have higher revenue. However, from the revenue per dollar invested, the orange squares become more profitable. Now the question is why the orange squares are more profitable per dollar invested, although people should pay more if they step on your properties on the green squares compared to the orange squares. I would like you to think about this based on the Monopoly game itself, the rules in the game and everything, and then try to relate it with the steady state probabilities that you see here. So that's the end of this video, and then in the next one we're going to talk about another concept in the that is still related to steady state probabilities. So see you on the next one. Thank you.